So my job is basically to support researchers with their mainly analysis and design, but I also sit on the AWEB committee, and I have a bit of a wider view of reproducibility across the life and health sciences. I've been doing this about 5 years, and I've come across some sort of repeated issues in the community that I'm going to talk about today. Okay, so what I'm going to do is give you a little bit of an overview of the common problems and issues that I see all the time and which I frequently get asked about. And these are my sort of 7 sins, if you like, of experimental design and statistics. They tend to be what I deal with, but they're kind of issues that relate more widely to biosciences research in general, and they're not just specific to Bristol. I sort of laid them out in order of the experimental journey, from the design stage through to the analysis stage, and then your interpretation and presentation. So I'm going to go through each of these in turn, highlight the major issues, and then provide you with some solutions. Okay, so the first sin is insufficient knowledge about your sort of sample background population. So whenever we're taking samples, what we're aiming for is a random, representative, targeted sample of what you're trying to study. But actually this isn't always the case. So if you work with any kind of population that you breed on site, if you work with insects or fish or something, you'll purpose breed a population, and what that means is that you know exactly what conditions the population has been bred in. So I used to do a lot of work with Drosophila. I could tell you exactly how many generations of culture I'd had before the experiment. I could tell you what the humidity, temperature, and all of those sorts of things were relative to the population. But actually that isn't always the case, and some people bring their samples in from perhaps external suppliers, people that supply mice and rats, or perhaps blood donors that donate tissue cultures and cell cultures and all that kind of thing. And so in those circumstances, it's not as easy for you to provide the context of your population of samples. And so it's less easy for you to then imagine what other kinds of biases and confounders might be creeping in before you actually get to the start of the experiment. And so the solution is for you to really gather as much information as you can before you start, and make sure you understand exactly what the targeted population was. Because so a recent example of where this is very relevant is a zebrafish conference that we had in Exeter recently, where it became very apparent that the housing and husbandry conditions of zebrafish research vary widely across the community. And so this is probably contributing a lot to why we cannot reproduce results from lab to lab and across time. So that's just something to be aware of. Okay, the next sin, but inappropriate maybe randomization and blinding. So randomization and blinding is of course the absolute crux of experimental work, and if it's not applied properly, of course you're not controlling for biases and confounders, and you're perhaps invalidating the very work that you're trying to produce. So the nice concept of randomization and interspersion was outlined in this paper by Stuart Hurlbut in 1984. And he produced this very nice schematic to help us just conceptualize really what we're aiming for. And he said, just ask yourself a very simple question: what would happen in each of these designs if there was a chance event during your experiment? Let's imagine there was an environmental gradient in light or temperature, an accident in the lab. Which of these designs would be affected the most? And you can see, of course, in rows A1 to 3, if there was a chance event, let's say at the right-hand side of the picture, a few data points from different experimental groups might be affected, but really the risk of bias is spread across your experimental groups. Whereas in groups B1 to 4, if you had any kind of chance event or accident in the lab, you can see that one group is going to be biased more than the other, which is pulling away your mean values of treatment and control off their true values. And of course in the bottom row you've just not got any replication at all with which to do any kind of analysis. And so the solution really is to think about where and how you need to randomize and blind your subjects or samples in the experiment. And I'm talking about not just the treatments, but the procedures, the how and the when, so that we don't get things like order effects and time of day effects and things like that. Okay, so moving on to the analysis phase. The most common thing I get asked about is what test do I need? And this is often at the point where the data set already exists. And I'm going to say right now that is too late in the proceedings. You should have already figured out what analysis you should need to do before you collect the data. You should be running dummy data sets ideally, and you should be thinking about which is the best approach. Quite often I find that the ambitions of the experiment outstrip the statistical training of the researcher. Okay? So that they're not aware that there are many different approaches that you might take. There's a huge menu of choices that stats people have been very hard at work for you, making on your behalf. But it's up to you to be clear about which one fits the data and which one is the best approach. Okay? So the solution really, I'm afraid, is on you. You need to make sure that your statistical training matches your ambitions and just be aware of the different approaches that you can take. And also it's in your interest because it gives you more confidence about data analysis, and it gives you more context and more explanatory power. You can explore your data in many more ways. All right, so quite closely related to that is this big issue of pseudo-replication. Okay, it's related to the randomization issue, and it's related to inappropriate analysis for the data. The range of circumstances in which you can apply basic statistical tests are actually quite limited. And more often than not, I'll come across designs where there have been multiple measurements made on the same things, or there have been data points taken from clusters of samples which require a different statistical approach. And for a very good reason. If you measured 10 mice 3 times and put 30 data points into a t-test, what happens is the standard error is too small. It's smaller than it should be relative to a random independent sample. And what that means is you're more likely to produce a small p-value that then of course gets published and then perhaps might not be reproduced by somebody else doing it perhaps in a different way. So the solution is really to understand the correct unit of replication for your actual hypothesis test that you'd plan to do. And it may well be that you need to upgrade again to tests of related data points, repeated measures ANOVA or longitudinal style testing, or it may be that you need to take a hierarchical approach. And some people are very adept at doing this, they're very aware of these issues, and some branches of biosciences are completely unaware of this. So it kind of really is an issue that we need to tackle. All right, the other sort of bread and butter for me is statistical power. Many people are not really aware of the concept of statistical power. So statistical power is literally just the likelihood of reaching the significance threshold given a particular effect size and a particular sample size and a preset p-value. And I've sort of presented this concept of a microscope here for you to try and sort of understand that it's a little bit like setting up a recipe. Okay, we pick different parameters and we set those things to make sure that the experiment works how we would need it to in a statistical test. So the most important feature is the effect size. This is the difference between the mean values of your treatment and your control group, usually on a standardized scale. And this is like the actual thing that we're trying to see on a slide. The statistical power is like the big magnification that you might choose, 10, 20, 80, whatever. The p-value is equivalent to sort of the threshold, the eyepiece that you choose to look down to accept a significant result. And the sample size is like the fine-tuning focus that we use to sort of bring all this picture together and to make sure that if there is a difference, and we've got the statistical sample size to see it when we apply a statistical test. Okay? There's a little bit of an over-reliance on p-values to tell us when something is made a difference or not. The p-value is just the confidence that you have to throw away the null hypothesis. That's it. It doesn't mean anything more than that. Okay? What we need to do is understand the effect size difference and the statistical power that we had to find it in a statistical test. And I'm just going to kind of expand this concept a little bit because it really is kind of a bit of a crunch point. So the distributions on the left demonstrate the difference between your control and treatment groups, your effect size difference. The graph on the right shows you how effect size, statistical power, and sample size all work together to achieve statistical significance. So on the left-hand side, you've got your effect sizes running from 0 to about, well, 1 is quite a large effect size. So you can see the dotted line shows that for an effect size of 1, you'd need a sample size of 30 to have a statistical power of 80%. 80% chance of reaching a small p-value in a statistical test. And you can see that if you had an effect size smaller than you anticipated, around about 0.5, you'd need to up the sample size to 120 to maintain that same power. If you choose to stick with the same sample size of 30, you can see that you'd lose statistical power. So you'd have something like a 30% chance of finding a small p-value in a statistical test. And it then becomes up to you whether you think it's worth running that experiment given the costs and time and all the rest of it. Okay, so moving on to sort of the interpretation phase of things, there's a little bit of over-interpreting the data going on, okay? So we have a very well-established hierarchy of evidence in biosciences where things like case studies and observational studies rank lower on the order of convincing us than randomized controlled trials and then at the peak, meta-analyses or reviews of the data. And we've got a little bit of an issue where perhaps studies that were conducted quite low on the order of hierarchy get a little bit over-interpreted and presented as if they were actually quite high up. And what happens then is we can't reproduce results because the foundations of the original methods and analysis did not support that level of confidence in the results. And so one of the solutions is to be clear about where the limitations of your data are. Where do you sit in the hierarchy? What real biases and confounders actually occurred during the course of the experiment? Because we all know things don't go to plan. And the requirement is to actually be quite open about that and admit when things kind of went wrong or didn't go as planned. And be clear about what the data supports. If you have an N of 1, you have no statistical degrees of freedom to make any inferences beyond that top level. And we can't translate, we can't generalize beyond that data. Okay, and finally, insufficient detail to correctly interpret the results. So this is kind of, I think, a big one, and one that we can all kind of really try and do better at. So recently I undertook a review of publishing at University of Bristol. I used animal researchers and I took all of the publications that we see in the AWEB committee and I scored them for their compliance with the ARRIVE guidelines. The ARRIVE guidelines are a set of logical checklist publication guidelines for animal researchers, but really they're useful for everyone. And well, you can see on the left-hand side that there was quite a wide variety in the scoring of these papers. So some papers scored quite highly and produced, ticked off most of the requirements of the list, but actually perhaps a worrying amount of papers had less than 50% of the available scores. So they produced less than 50% of the information needed to actually interpret the study properly. And when we've had large reviews by our sort of House of Commons Science Committee and in the US National Academy of Sciences, one of the major reasons for a lack of reproducibility is we just simply can't understand what's been written. We cannot reproduce the experiment quite literally because there isn't enough information. And so this is clearly an area where we can all sort of think about how we're writing things and be aware of these guidelines. So on the right-hand side, just to let you know what kind of difference this makes, those are agreement scores between myself and NC3R's reviewers, and you can see that only 3 of the scoring criteria actually had a high agreement, and all of the other criteria were sort of a bit shaky, which means basically readers, this is a high risk of readers actually not understanding what's been written in a paper, because there just simply isn't the context and the information that we need. And so I suggest really the solution is for us to all be aware of these guidelines. They do exist, and there's a nice little collection of them now. Some of them relate to animal work, some of them relate to statistics and randomized controlled trials and things. So this is one area where we can all sort of, I think, up our game a little bit. Right, so there's my 7 sins and my 7 suggestions. Not all of them will resonate with you. Some of them might be sort of, you're quite confident that you don't fall into these traps. But if you do need a bit of guidance or you need a bit more information about these things, there's a growing army of professional support with Fiona, Nick and myself for starters. There's a reproducibility network at the university. There are lots of tools to help you. So there are statistical calculators to help you calculate power and sample size. And I suggest really it's all in all of our interests to start being aware of these and to use them, because reproducibility is becoming the point about getting funding, ethics approval certainly here, and even publishing. So don't stay in the dark about it. So this is just the final slide of resources and information. I do have some pages on the Life Sciences SharePoint site, and there's my contact details for anybody that would like any sort of more advice about these sorts of things. I'm quite happy for these slides to be shared afterwards. These are just some key papers that I suggest that you might like to look up to understand some of these really key issues about pseudo-replication and power and that kind of thing. Okay, that's it from me. Thank you.